Hello everyone, my name is Yiwen Elsa Cheng. I am a ninth grader from Harvard Westlake School in Studio City. Worldwide, more and more elderly people struggle with walking due to various conditions, which creates pressure on the healthcare systems and caregivers. Personally, both my grandmothers face mobility challenges due to Alzheimer's and NIID. Seeing them struggles make me realize the current mobility aids are not enough. Nevertheless, each existing solution has major limitations. My goal is to create a robot that provides real-time support, affordable, and enhances independence. Inspired by autonomous vehicles technology, my hypothesis is to adapt driverless technology to my robot to detect obstacles and assist users, and use the human body keypoint technology for recognition. Starting with my PCB, I distributed multiple GND connections on different connectors and separated different types of signals into different connectors considering the balance of power distribution and signal isolation, and the ESP32 is also placed on it. Then, the circuit expansion board manages all the wires. Finally, my design of the two touchscreens allows the user to interact with the robot easily. One of them is a camera image display, and the other one is motion status display, which shows the speed. Then, I started with a standard 4-wheeled walker that I brought, kept the two original universal wheels, and replaced the other two with motors with the attachments I designed, which I then connected to my PCB to control the speed. The pressure transducer is placed on the right-hand side only so that the user's other hand can do other things, and the binocular camera is fixed by the mobile phone holder. Last but not least, the AI system starts with the camera collects a video containing the user's body as the original data. Then MediaPipe human body keypoint detection is used to calculate the XY coordinates of 33 human body keypoints as the original data. Then it will be labeled with a total of 4 categories: 0, normal, 1, backfall, 2, rightfall, 3, leftfall. The next step is to set the sliding window. Predict the next 1 time step every 10 time steps. At this place, I also added the gyro data, which I think is very important because it ensures that even if the camera is blocked, it can continue to predict and run the program. Then, the next step is to use maximum and minimum normalization. Finally, the model structure is a layer of LSTM, which stands for long short-term memory, and the layer of full connected layer, which is used for feature extraction and information transfer, and is classified based on the 4 labels. In conclusion, I turned single modality data into multiple modality data, which creates more accuracy. I did the straight line walking test by placing tapes on the floor that were 1 meter apart. The results shows that the most stableness occurs during 0 to 1 meter, which won't be a sudden startup that catches the user off guard. Using the same setup as the straight line walking test, I did the left and right turn test by pressing the turning buttons on both sides. While both left and right turns showed smooth transitions, the results showed that right turns took slightly longer than the left turns, and had a small but consistent increase in completion time. These inconsistencies are likely due to I am right-handed and a single pressure transducer. I then take the circle that had a diameter of 1.6 meter and walked at a default speed. The results showed stable motion with minimum deviation between checkpoints. The initial phase, 0 to 1, took a little longer, but the time remained stable after that. Interestingly, clockwise movement tend to be more precise and consist than counterclockwise movement. These findings in the circular movement test are consistent with the other 2 tests. The accuracy curve graph shows a significant difference between the 2 curves, which means the model is overfitting. While it performs beautifully on the training data, it struggles to generalize to unknown data. The ROC curve graph showed a good performance since the area under each line is large. This means fewer false positives and all are true positives, which is a reflection of the strong robustness of the system. These test results demonstrate that my robot successfully enhances stability, adaptability, and endurance in various movement scenarios. And I believe my robot can help users improve their independence and confidence while reducing the pressure of the care systems in the real world. My future improvements will focus on refining the AI model to handle and detect a wider variety of users' behavior and improve adaptability. Thank you for listening.